And now we start a new series of talks, first on bubble chambers and then on axion detection by Andrew Sonnenschein. I don't know if I'm saying correctly, from Fermilab.
Thank you. Is this audio okay?
Yeah.
Well, we're really keeping things moving along here. No coffee break or anything. After this, okay. So I have this I hope fun talk about bubble chambers. I'm sure you've heard a lot about dark matter over the last week. I've been watching the talks on the movies that are posted on the web. Well, okay. Let's see if I can get this thing to... Well, I'm just going to advance it manually. But you haven't heard, I'm sure you haven't heard about anything about bubble chambers, because bubble chambers are, for a long time, were thought to be useless for anything in high energy physics, for reasons that I'll explain in a minute. But just to go back, because it's an interesting history, just to go back a little bit, the bubble chambers were invented by this guy, Donald Glaser. Oh, Martin, could I get that back just for the laser pointer? Oh, here's the laser pointer. So Glaser, this was the 1950s, and Glaser was a cosmic ray physicist working, going up to the top of mountains with cloud chambers and looking for cosmic rays interacting in cloud chambers. And that's a very frustrating activity, because a cloud chamber is a chamber full of water vapor, which is saturated, and so when a cosmic ray goes through it, there is condensation of water along the charged track, and so you can then take a picture and visualize the track that way. But it's a gaseous detector, and so there are not very many interactions, and they didn't have computerized, recording of the chamber images, so very few images had anything interesting in them. So he thought, I'd like to develop a similar system that has a solid target, or a liquid target with a high density. And so he started building these chambers which had a volatile liquid. In this case it was ether. He actually put beer in some of these chambers in the initial development, because he wanted something, that the carbonation acts like a saturation. It's a very similar effect. So, but the chamber that was successful, the first one, was filled with ether, and he warmed it up to get a high vapor pressure in the ether, and then released the pressure, suddenly reduced the pressure, and then he could see these particle tracks from a muon, I guess, in this case. But interestingly, Glaser he won the Nobel Prize for inventing the bubble chamber, but he didn't, he actually wasn't the key person in developing it for doing real experiments. Actually, his dream of using bubble chambers to do cosmic ray experiments was never really realized, because there was no way to get good triggers on cosmic rays. So actually, I guess that you could say that our work on trying to look for dark matter is the new cosmic ray physics, and that maybe we've come the closest in these bubble chamber searches for WIMPs to realizing that idea of using them for cosmic ray physics. But what really happened was this guy, Louis Alvarez, who was a senior scientist. At this point, Glaser was junior. He was an assistant professor, and Alvarez met him at the first meeting of the American Physical Society, where he was presenting his new bubble chamber results. And they sat down at the lunch table on the first day of the conference, and Alvarez asked him, "What are you going to show?" And in this fateful meeting, Glaser told him everything before he even gave the presentation. And then Alvarez, who was more senior and knew everyone in particle physics and was working on experiments with cyclotrons at Berkeley, went back to his hotel room, called in his whole team, and they started scheming about how to build this into a large apparatus that could be used for real experiments. And so within 7 years, they went from that little test tube on the previous slide to this gigantic thing. They got the money but they went to Washington D.C. with Alvarez's boss, Ernest Lawrence, the famous Ernest Lawrence, who invented the cyclotron, and they got the money the same day to build this big thing. And so this is just 7 years. They went from a test tube to this huge apparatus. And there's a great quote here. In those days, if you had a good idea and people thought it was a good idea, and he had a lot of credibility because of his work on the Manhattan Project and the whole history of the development of particle physics, then he just got the funding. So I'm going to recommend this. This is a book recommendation. Alvarez, Adventures of a Physicist. You can buy it used on Amazon for $2.50. But this is the best autobiography of an experimental physicist. Theorists may prefer Feynman's biography, but this, Alvarez invented 3 different kinds of radar in the war, and then went on to, he was an amateur pilot, and he went to the Manhattan Project, and then worked, the radar wasn't enough for him, then he worked on the bomb, and he worked on many other things. The extinction of the dinosaurs later in his career, the X-raying of the Egyptian pyramids with muons, and other stuff. So this is really terrific. I highly recommend it. Okay, so back to bubble chambers. The bubble chambers, of course, were valued, and in the popular imagination, actually, they capture much of particle physics because you've got these very detailed tracks, which are still more detailed than what you get from modern electronic detectors, except near the vertex, for example, of Atlas or CMS, where things are very pixelated. You get very accurate information near the vertex, but over the whole volume, you get much less information. So you have these wonderful tracks, and of course, there's a magnetic field. So positive particles turn one way, and negative particles turn the other way, and from the curvature you can reconstruct the momentum. So you have all the information you need just from this very simple device where you just reduce the pressure and take a picture without billions of electronics channels and computers and everything. So this was wonderful, but of course the technology is not used anymore in mainstream particle physics, and this plot goes a long way to showing why that is. It's from Alvarez's Nobel Prize lecture. He got the prize a little bit after Glaser, after doing the real work of turning these things into valuable instruments for doing particle physics. So here's events per year from these are different automatic devices that they use for measuring the bubble chamber tracks here. So they had various generations of track measuring machines, and this is like the number of people working on measuring tracks, which went up to about 200 by the end of the 60s. And so they started out with like a couple of, being able to analyze a couple of events per hour, and ended up in 1967 being able to do 1 million events per year. So in comparison, the LHC beam crossing rate is 40 megahertz, and there are about 10 interactions per crossing. Bubble chambers can't be triggered. You have to accept every event that happens. And so, in some sense, in 1 second of LHC operations, you've accumulated more events than you were able to get in the whole history of bubble chambers. And you're able to analyze them because of the tight coupling to computers, which was never achieved for the bubble chambers. And part of the problem here is that bubbles actually take time to grow. They take about 100 microseconds to grow to a size where you can photograph them. And in that time, a lot of stuff has happened. So that's just too slow for a real particle physics experiment. So nowadays, the main role in particle physics of bubble chambers is that they're lawn ornaments at national labs, both in Europe. This is the famous Gargamel chamber that was used to detect the weak neutral currents, so the first measurement of the Z, in some sense, producing neutrino events. This is just a piston from the bottom of a huge chamber that was operated at Argonne. Think about how big that was. And this is the largest big hydrogen chamber that was working into the late 80s at Fermilab, doing neutrino experiments. So if you think about it, the neutrino experiments are the niche where the bubble chambers still remained useful after their heyday because the event rates were very low. And so into the 1980s, bubble chambers were still useful. And this chamber at DESI, which I just found a month ago at a dark matter conference, this probably has the most personality because it's got a little mouth and some eyes and stuff. So I don't know if there are any bubble chambers in South America, but all the old National Accelerator labs have them. Okay, so then we got the idea of using bubble chambers to search for WIMPs, and some of the reasons are, okay. Well, here's a list actually of your ideal characteristics that a WIMP detector would have. You know, after Tali's talk, that you need to have a big target mass in the future. Well, even now, when I first started giving these talks, we were at like 100 kilograms. Now we're at a ton, and soon we'll be at 10 tons, with people dreaming of 100-ton dark matter detectors. So you need a big instrumented mass. You need fairly low energy thresholds. At least 10 keV is the largest you could reasonably have. And for looking at the light WIMP models, which have become popular in recent years, you'd like to go down even to sub keV energy thresholds. Ideally, you'd be able to look at multiple target nuclei. I think actually Tali introduced this subject in a better way than I can possibly do, with all of those slides showing the different rates on different nuclei and the different backgrounds from neutrinos on different nuclei. You'd like to achieve no background from environmental radioactivity, which was very challenging. You'd like to measure nuclear recoil energies on an event-by-event basis. And you'd like to measure the recoil direction, so you can get the directional information that Tali was also talking about. So here's the scorecard for how bubble chambers potentially can do. Large target masses were already achieved in the 1960s, so that's good. Surprisingly, because old bubble chamber physicists were surprised we were trying to do this, because when you think of those older experiments, people are looking for tracks, and they're typically hundreds of MeV or GeV energies to produce these tracks. And so no one had ever tried looking for one bubble in a bubble chamber. The surprising thing is that the energy to produce just a single bubble is very low, even though in practice the chambers had thresholds of tens of a GeV or something like that. And I'm going to talk more about this in a moment. And then here's where here's really these days where the bubble chambers sort of come into their own, is that the possibility of instrumenting multiple target nuclei within possibly the same detector system. So we've done this. We've put in CF3I with iodine and fluorine as the target. We've run also with CF3Br, another refrigerant gas with bromine as the target. We've considered also hydrogenous liquids, and there are other alternatives. So there are even some nuclear physicists who want to use oxygen-16 as a target for producing gamma alpha reactions. So the versatility of the different liquids that you can load into it is very important. Actually, almost any liquid you can imagine pretty much can be made into a bubble chamber. Every liquid has a vapor pressure and a heat of vaporization, and those are the things you need to know to make a bubble chamber. Some liquids are dangerous, need to be heated up to high temperatures, which is dangerous. So there are some practical aspects, but you can put, if you really cared, you could put a large fraction of the periodic table into some kind of bubble chamber by making it into a liquid. And we don't do so well here. I'm going to talk a lot about environmental radioactivity, where we do a wonderful job rejecting gamma and alpha radiation from the environment. The individual bubbles don't have information about nuclear recoil energy. That can only come by their threshold devices. If you're over a threshold, you get a bubble. If you're under, you don't get a bubble. So you can only accumulate an energy spectrum by scanning the threshold over time, which means effectively a reduction in your exposure. So with some caveats, you can get nuclear recoil energies. And nuclear recoil direction, everyone always asks, well, what about the shape of the bubble? Is there recoil direction information? Some people think there might be and are doing R&D to do that, but so far the answer is no recoil information. Okay, so since the important point is that we have flexibility to use different nuclei, it's probably helpful to remind you generically what the main types of nuclear couplings you're looking for in WIMP searches are. I think that previous speakers have covered this, but so you'll recall that so this is just a simple summary. You'll recall that the de Broglie wavelength of a Wimp that is scattering on a nucleus is of order nuclear dimensions, around a femtometer, when the Wimp generically has mass of 100 GeV and has a typical velocity of a particle coming from the galaxy halo. So there's some measure of coherence of the interaction across the nucleus. You have to sum up the amplitudes for scattering on each of the nucleons in the nucleus, and you're coupling to the collection rather than to the individual nucleons. At high masses and high speeds, where this gets small, where the wavelength gets smaller, that's no longer entirely true, and there's a form factor that comes into it. But for low masses and reasonably low velocities, there is coherence. So imagine how this works. If you have spin-independent coupling, which is the one that most experiments are looking for, then all of the nuclei, all the amplitudes from the in the nucleus, they all sum up, and then you square the amplitudes, and you get this A squared enhancement factor in the cross-section, which allows you to measure cross-sections that are around 1,000 to 10,000 times smaller than if you had to couple to individual nucleons. So in order to do the best job on this, you want high A targets, large atomic mass, like, oops, I don't want to answer that. So like germanium and xenon, and in bubble chambers, iodine is what we use. On the other hand, for spin-dependent scattering, since in the nuclear shell model, the nucleons are arranged in opposite spin pairs, and so the spin pairs, they cancel each other, and all you end up with is a coupling to the odd nucleus that's out, the odd nucleon out. So you'll have the last nucleon will be either a neutron or a proton and will be unpaired, and you effectively couple to that. And so to be sensitive to this, you'd like to have totally different nuclei. And actually, with form factor considerations and isotopic abundances considered, the best one for this is fluorine. So bubble chambers, we get a lot of mileage from having fluorine as an available target, which isn't available in any other kind of detector. Well, there are some gaseous C3F8 directional detectors that also have fluorine, but not very much of it. So it's really having the fluorine target is tremendous. But even for spin independent, suppose we saw a signal, the first thing you'd like to do if you see someone says they thought they saw a spin independent dark matter signal, you'd like to measure the A squared dependence that's supposed to be there, and for that you would need multiple targets, nuclei. So it's good to have an assortment of different nuclei you can put in there. And as I mentioned, fluorine is the best for spin dependent. If you want to go to light mass, you would need a kinematic match between the dark matter particle and the nucleus, and so hydrogen would be very nice for light WIMPs. So if we ever detect a dark matter signal, the bubble chambers will become really important because of this ability to separate out, to measure the A squared dependence and to separate out the different nuclear effects like spin dependent versus spin independent. Another important thing that Tolly actually has better figures than I do. I need to borrow some of his slides, but because the backgrounds are coherent on the nucleus, in the spin dependent case, we actually have we have a much lower neutrino floor than you have in a spin with a larger nucleus. So ultimately the spin dependent neutrino sensitivity limit is going to be lower for fluorine than for something like xenon. Okay, so all of these great things would be they would be useless if you were unable to achieve low backgrounds. I like this, even though this figure is a little bit antique, I like it because it illustrates what you're up against. If you exposed a unshielded detector in this room, you would have something like many events per second, and just from environmental ambient radioactivity. If you do a good job shielding with conventional lead shields and things like that, you get down to about an event per minute. And then you have to start reducing the radioactivity of your apparatus. So this shows how Ron Brodzinski, who was a pioneer in the field, working with Frank Avignoni in the early years, by reducing the radioactivity of the detector, achieved something like a 5 order of magnitude reduction by replacing stuff in the detector like an indium contact and replacing the copper with special copper and the lead with special lead, and eventually work down to this very low background rate. But even if you do that, there's a limit to how far you can get. So we're well past the point of diminishing returns on reducing the radioactivity of components. We need some kind of physics mechanism to reject events that are due to gamma rays, neutrons, and not to nuclear recoils from WIMPs. So it turns out that bubble chamber physics has a mechanism for this already baked in. And to tell you about that, I need to talk a little bit about the physics of bubble nucleation, which I guess is really more chemistry than physics. So bubble chambers, so here's a typical phase diagram for some substance like in high school chemistry, where at high pressure and low temperature you've got a solid, at high temperature and low pressure you've got a gas, and somewhere in the middle you've got a liquid, and this is the liquid-gas phase boundary. So bubble chambers always start somewhere up here in the liquid, and you have a piston which reduces the pressure rapidly. You cross over the phase boundary, and you're in a region where there's metastability. The liquid wants to turn into a gas, but it's frustrated from doing so on short timescales. And then it does eventually, a bubble's nucleated, and then the bubble chamber works in reverse. The piston raises the pressure and converts the gas back into a liquid. So what is this frustration? What's the origin of this frustration of the bubble nucleation once you cross the phase boundary? Well, so all of the liquid, when you depressurize, all the liquid now wants to turn into a gas. But in order to do that, it has to start at some particular point. And so a bubble has to form. And if you analyze the energetics of a bubble, bubbles have surface tension at the liquid-gas interface. And they have an internal pressure from the vapor pressure of the liquid that's forcing it to, that's working in the opposite direction, forcing it to expand. And there's an equilibrium condition. There's a critical radius, which is just the ratio of the surface tension to the difference between the vapor pressure and external pressure. If bubble is smaller than this critical radius, it just tends to shrink. And if it's above the critical radius, it will grow without any limit. So there's a critical radius here, and there's a critical energy, which is the energy you need to do the work to expand the bubble to the critical radius. And after that, the liquid takes over by itself and doesn't need any help, and it just gets bigger and bigger. So you need to deposit energy in this critical radius, enough for the liquid to get over the critical energy hump. And that's the energy that has to be deposited by an ionizing particle going through the liquid. So you can it's wonderful, you can explicitly calculate what's the size of this energy barrier, and you can make plots of it versus temperature and pressure, and these are the energy thresholds you get in keV. So for example, at I guess 40 degrees and 20 degrees and 20 psi, you get something like a 5 keV nuclear recoil threshold. So that's wonderful. It shows that the bubble chambers were intrinsically low energy devices. The energy to nucleate one bubble is rather small. And then there's also, at the same time, that energy has to be deposited in the molecules that will eventually make up the bubble. So it has to be deposited on a length scale that's similar to that critical bubble radius. And so that makes the threshold actually a two-dimensional thing. There's a energy dEdx threshold, the track energy density, that's one threshold, and then there's just the total energy, that's another threshold. And so by setting the temperature and pressure of the liquid, this is another example using CF3I, one of our targets as for the calculations, you're picking a quadrant in this plot. So like up here, if your pressure was 65 psi, none of these particles would be able to do any bubble nucleation. Neither electron recoils may have high energy, but they have low dE dx, or not even alpha particles or the most heavily ionizing things like the recoil of an iodine nucleus. Up here in this quadrant, none of that can nucleate. There shouldn't really be any bubbles at all in the liquid. If you go now to this lower pressure, you're in the green quadrant, and all of a sudden all these heavily ionizing things, alphas from radon decay, carbon recoils, iodine recoils, fluorine recoils, they can produce bubbles, but the electron recoils, which are the main background, gamma ray comes in, Compton scatters on an electron gets pushed into the liquid. That's a typical background in a dark matter detector. No bubble nucleation there. If you want to operate in the mode where the classic bubble chambers worked most of the time, then you would go even to lower pressure or higher temperature so that you became sensitive to these electrons, and then you would start to see tracks from charged particles. This was, by the way, known in the classic bubble chamber era, and as evidence, I point to this paper from 1969 from a small propane chamber that was built for some purpose that didn't work out, having to do with counting carbon-14 beta decay. But what they did is they measured they measured rate with a lot of background radiation from the environment incident on the detector. They measured rate as a function of pressure, and they see these plateaus corresponding to the dE/dx threshold. So at low pressure, there's the heavily ionizing things come in, and then you go higher and you get a little bit lighter ionizing things, protons, which are actually nuclear recoils in this detector. The liquid was propane, which is carbon, hydrogen. So the protons were the hydrogen recoils from neutrons from the environment. And then if you go to higher vapor pressure, you start to see gamma rays up here. Now even then, if these people had known about WIMPs in 1969, they could have just decided to run their detector at 100 psi and been sensitive to proton recoils, insensitive to gamma rays, put this in a mine with some shielding around it, and you would have a WIMP, you'd have a limit on WIMPs. And actually this should have been known when the field started up in the 80s. Somehow this was forgotten for a decade, and people went and did crazy things like building cryogenic detectors and all of this other technology. So I claim if they had remembered, if the bubble chamber physicists had engaged, they were all reaching, in the 1980s, they were all sort of reaching retirement age, all the people who knew this stuff. So there was maybe an opportunity that was lost. Okay, so how well does this work in practice? It works in theory, but how does it work in practice? It works extremely well in practice. So here we expose our chambers to some of our chambers with CF3I and some with C3F8 to very high gamma ray fluxes, and we measure very small nucleations per gamma interaction in C3F8, which is the best, on the order of 10 to the minus 10 of bubbles per gamma interaction. So that's way better than you get from any of the other technologies, I believe. So we started playing with this. Technology, and originally started building small detectors like this, which was a test tube, and this is sort of a repeat of Glazer's technology development, but with a different focus. So he started with a little glass test tube, and we started with a little glass test tube, and there's our volume of CF3BR. It was in this case, and there was a piston, very simple device. Piston, depressurize the liquid. I'm just showing you how simple this is. Camera, take pictures, take a video, and you got to pay attention to cleanliness because rough surfaces trap gas bubbles, and then when you depressurize, you get bubbling off these surfaces. But if you do a good job cleaning, then you depressurize and nothing happens, and you wait, and eventually pop, you get a bubble from usually from a neutron. So here, let me see if this video will start. We took some high-speed videos. Okay, there it is. So this is one frame at a second. We had a high-speed video camera, and you see the bubble starts and just keeps on growing. I showed this video because people always used to ask in these talks, well, what if a bubble happens and you don't see it? Could you miss it? The point is that the bubbles just keep on growing and growing. You can't miss them. It wants to turn the whole test tube from liquid into gas, and so you get an enormous signal based on this bubble nucleation amplifying process. Unfortunately, no sound in this video. The sound is pretty cool. Also, we should put that together. Oops. Okay. Okay. Good. So we had to develop some optimizations of bubble chamber technology for Wimp searches. The conventional bubble chamber is a high-speed device. Remember that you're always limited by the rate at which you can take data. That was, in the end, what killed bubble chambers. So you want to make it as fast as possible. So this shows the duty cycle of an old-time hydrogen bubble chamber at SLAC. And it shows that the depressurization here was very fast in a few milliseconds. A few more milliseconds later, a beam arrives from the accelerator. The timing of that is locked together. The bubble starts to grow, and then bam, you recompress. Then maybe 100 milliseconds later, you do the whole thing over again. So this is a bubble chamber that is synchronized with an external beam that's coming at a specific time. So in the case of cosmic rays or dark matter, you don't know when the particle is going to arrive in the bubble chamber, so you have to do something different. And this had never been done before. So what we did here is we made the chamber so clean that there were no sources of internal bubble nucleation. We depressurize and we can hold the low pressure for as long as hundreds of seconds, even hours in some cases. And then after some period of time, an event happens, perhaps due to a neutron, maybe due to a Wimp, and we see the event with a video camera, and then we send a command to the piston telling it to fire. So this is a triggered operation of the bubble chamber, which was never achieved by Glaser. And then another optimization was to protect it from environmental neutron radiation. So this is kind of a cartoon of what all the chambers end up looking like. There's a big volume of water which shields against gamma rays and neutrons from the environment. And then we have a construction detail of these chambers is that we have a superheated liquid which is heavier than water, and we have a water layer floating above the superheated liquid. The water layer communicates with mechanical components like a bellows to control the pressure. And so there are all this superheated liquid target sees is a envelope of glass or later on ultra high purity fused silica with very low radioactivity in it. And that's all. It just so if you're a molecule of CF3I, you just see smooth water above you and smooth glass on the sides. You don't see any bubble nucleation sites. And then this is a small chamber, so you can see how some of this worked out in reality. There's the target liquid. This is the glass vessel, which is the size of a wine bottle. There's mineral oil, which is a hydraulic working fluid, and a neutron shield at the same time. You cycle the pressure, and you take pictures through this window, and that's all there is. That's all there is to it, really. And you get beautiful images like this. This shows a neutron scattering 3 times. So one of the great things about this kind of detector is you have the best spatial resolution of any dark matter detector technology. With stereo images, you measure the position of every interaction in 3 dimensions with sub-millimeter precision, and so you can tag neutron backgrounds by the multiple scattering. So that's great. You can never be confused by a neutron background looking like a Wimp. So here's an example of a large chamber, Pico 60, which is where all of our published results come from these days. So this is a conventional steel pressure vessel. Since the discrimination against gamma rays is so large, you don't need fancy specialized construction techniques or materials. You use basically a commercial vendor can supply most of this equipment, and it's not radioactive enough to produce any bubbles. And this is the inner vessel is where things get a little more difficult, because then you're close to the bubbling liquid. And so the critical piece is this fused silica vessel, which is made usually for the semiconductor industry. My understanding is for some kind of flat panel display manufacturing process where impurities are important. So this is the hard part to get and may ultimately limit the size that of bubble chamber we can make. This is like what the whole system looked like during testing at Fermilab quite a few years ago now. There's the plastic water tank and the pressure controller and so on. Okay, so now I have to tell you about one other background issue. Now, so I told you about neutrons, I told you about gamma rays, but going back to this plot, you'll remember that besides nuclear recoils from iodine, which might be your signal, or from fluorine if you're looking for spin-dependent interactions, there are also alpha particles from radon, and there are the daughter, when radon decays, it has a daughter, polonium-218, which the nucleus is ejected in the opposite direction of the alpha particle, and that's even more heavily ionizing. So this is a problem. In this quadrant where you're sensitive to WIMPs, you're also sensitive to alpha particles, and we thought that this would eventually be the limiting problem. In fact, in early, I guess more than 10 years ago, in early runs of small chambers, we found this very annoying background. I won't go through all the details of this plot because the issue is no longer current, but we saw this high rate. There were thousands of events per day of bubbles caused by alpha particle, radon, dissolved in the liquid. And we could tell that because there's a certain threshold for radon where alpha particles go away. Above that threshold, they don't have enough DEDX. And so there's this characteristic flat plateau of events versus pressure caused by radon. And this seemed like a really bad problem. Now, in some sense, if you just had better, if you just had much better cameras and a better optical system, you might be able to tell the difference between alpha decay bubbles and bubbles from nuclear recoils. Because let's suppose, just imagine, you have this imaginary optical system, which is impossible apparently to realize in reality, where you had 1 micron resolution over the entire volume of the bubble chamber, and you had, I guess you also need microsecond time resolution. So every microsecond you have to take this ultra high resolution picture. Then if you looked at a nuclear recoil, because a nuclear recoil has a range of about 100 nanometers, it would look like just one bubble. But if you looked at an alpha particle, you would see a whole bunch of bubbles along the track. So too bad that this can't be built in reality as an optical system. But what our collaborators found out is that actually the details of this interaction are recorded in an acoustic signal. And I'll show some plots of data in a minute, but you can imagine that this thing emits sound and this thing emits sound, but here there apparently are 5 bubbles that are emitting sound in the early phase of bubble growth compared to 1. So this could make a louder sound. And in fact, in about 2008, the Picasso group, which was another dark matter group using superheated liquids, but in a different form, they made a kind of mayonnaise-like mixture of superheated liquid with normal liquid, so little blobs of superheated droplets in a oily substrate, where each little droplet was an individual bubble chamber. So a little droplet can boil without affecting the other droplets that are in the emulsion. This technology is actually still used for neutron dissymmetry. It's pretty clever. But anyway, they attached a whole bunch of microphones to read out their superheated droplet detectors, and they found that, wow, neutrons don't sound as loud as alpha particles. There was, unfortunately, in these droplet detectors, the distributions overlap at the 10% level, but alphas are louder than neutrons. And that was an effect that had not been noticed before. Later, the people came up with the justification that I showed on the previous slide. So we built bubble chambers and instrumented them with the same acoustic readout, and we saw the same effect, except much larger separation between the two populations, because the acoustics on those droplet detectors are crazy. The acoustic waves are bouncing all over the place and are attenuated. So it's very hard to get a clean signal. We were able to get much cleaner signals. This shows neutron recoils, and this shows alpha particles, and they're separated by many sigma. There's a little population here, maybe some indication of a problem developing. You see a little tail from the alphas. That look like neutrons acoustically. Those we assumed at the time were due to neutron, some residual neutron background in the room when we were doing the measurement. So this work is all, by the way, now done by the PICO collaboration, which is a merger of the previous Picasso and the previous Coup collaborations. So once the people doing the droplets discovered how much better bubble chambers worked for this measurement, we all decided to get together and do the same experiment. And it's done, all this work is done like a lot of the other projects discussed here in Snow Lab, which maybe some of you have been to. It's a fantastic place with Deep, Snow Plus, Pico, and Super CDMS, all located in the same area. We eventually moved our detectors to the big detector to Snow Lab. Shows the installation. There's the big fused silica vessel and this cool picture. We doubled up eventually on the number of cameras, so we have 4 video cameras reading the thing out. We discovered at some point that CF3I was photosensitive. It has some residual photosensitivity. We were delayed moving to Snow Lab because the CF3I chamber turned purple from the iodine being released into the water. And so we eventually had to play tricks, including moving to very long wavelength illumination to beat that problem. Okay, so we thought, okay, we've got it made. We've got gamma sensitivity. We can see the neutrons on an event-by-event basis. And we've got this acoustic alpha rejection. So we have no backgrounds. We're going to have the world's best. We thought we were going to beat liquid xenon for spin independent as well as do the best spin dependent measurement. But in fact, when we turned on, we saw all of these events. We saw eventually about 1,000 events in a 6-month run. We saw, and this was the weird spatial distribution where you had between 10 and 100 counts a day. There were large variations in the rate. So it clearly wasn't WIMPs. And there were other weird characteristics, like the event rate went up when the temperature changed. This shows that. Here's the temperature, and here's the event rate, and there was a correlation. So it wasn't dark matter. Unfortunately, acoustically, strangely, it looked almost like dark matter. The distribution of these weird events in acoustic power was very close. There was about a 20% excess power compared to neutrons, but these things also overlapped. So that was very annoying. And I won't belabor that point. There were also dependencies on how long the chamber was expanded. So the idea that we eventually came up with was that there must be something at this point that causes a bubble nucleation. And that something must be some kind of particulate material floating in the detector. And maybe then you could explain the distribution by the pattern of convection currents that happens as the temperature rises and falls. And so this looked to us a little like the expected convection current, where perhaps the particles were usually hanging out at the surfaces, like the water CF3I surface up here, and the convection currents were carrying the particles down the wall. And so we pulled all the liquids in the chamber out through filters, and we discovered that it was full, at least microscopically. You wouldn't see anything to the naked eye, but if you looked under a microscope, you would see that there were lots of little shavings of steel. So the parts of the chamber, so the stainless steel parts of the chamber were flaking off little bits of stainless steel. The quartz parts of the chamber were flaking off little bits of quartz. And that was the majority of what we would see. So whereas there was in total about 7 micrograms of quartz particles that we captured and 200 micrograms of stainless steel. So all of this stuff would kind of fit on the head of a pin. But nevertheless, there were large numbers of particles floating around in the liquid. And we actually we identified them also by using X-ray fluorescence. We learned about the techniques of the analytical chemists. They have wonderful ways of figuring out what the composition of small particles is. It turned out that data, even though we had that high background, since there were all these dependencies on the length of time the chamber was expanded, the 20% additional acoustic power, and the spatial distribution, by combining cuts, we were able to salvage the run and find a background-free region and produce quite a decent dark matter result at the time, which I'll show on a later plot. But the main thing we learned from this is we have to really clean this thing much better than we had been. And so we invented a system that has a recirculating spray jet with detergent that would go in there and then would spray, and a 4-pi would spray the inside of the vessel for hours and hours and hours, and we would monitor the effluent to see the particulate levels coming down. And we eventually did, you don't have to read the details of this, but this is like a size distribution of the remaining particulate that was in the liquid, which went down over time, and eventually we reached very clean conditions where we kind of saturated. And so then we ran again in 2017. After this very aggressive cleaning, we took data, and we were blind. At this point, we decided to use a blinding scheme. So we didn't, as we were collecting the data, we didn't know the details of all of those acoustic distributions. And then at the end of the run, we knew we had 106 bubble events that passed the basic quality cuts and acoustic cuts and were in the volume of interest. And then sort of on the fateful day, we unblinded and found that 0 of these events passed acoustic cuts. So all of these events were alphas. This is the region here. This is the acoustic power, and this is the region. The black is a neutron calibration. That's where you expect the WIMPs. But all those events turned out to be in peaks corresponding to alpha particles based on the acoustic analysis. So, wow, great, we're background free again. This was terrific. There was one little problem, which is that even though there were no events passing the cuts, which required just a single bubble, not multiple bubbles, there were 3 neutron events that were detected. So there were, they had high multiplicity, because when you get to a big volume like this, the neutrons tend to bounce a large number of times. So we had, I guess, a 5-bubble event, a 4-bubble event, and a 3-bubble event. And based on simulations, this was compatible with the non-observation of any singles, but the expectation was that we should see about 1 single event if we repeated the experiment. So we kind of discovered that even though we had done really well, we were saturating the dark matter limit that you could attain with this device based on neutron backgrounds, and we actually don't know exactly what was generating those neutrons, although we have some ideas. All of our estimates from radio purity measurements suggested that the background should have been a fraction of what was actually observed. But we got a really nice result anyway. This is the spin-dependent result from that Pico 60 run, blue. This is a combined exposure from all runs in brown. And this is a factor of 17 better than what we had done before. And for the first time, gets below the indirect detection limits from Super K and IceCube, which depend on, I don't know if these have been discussed at this meeting, but these limits depend on WIMPs being captured in the sun. The sun is made of hydrogen, which has a spin-dependent interaction. So based on that interaction, a certain fraction of WIMPs hitting the sun will be captured into a orbit that actually is inside the sun, and those then will encounter the sun more times, and they will annihilate. So they'll sort of condense down into the center of the sun, then the WIMPs annihilate into neutrinos, and you try to detect the neutrinos coming from the direction of the sun with these water Cherenkov detectors or ice Cherenkov detectors at the South Pole. So we, for the first time, got below this limit, which is a, these limits, there's some model dependence in these limits, but these are pretty good limits. So the real best physics definitely lies below the Super K and IceCube exclusions. And you can say that now the bubble chamber technique gets you into that region. We are now moving on to new chambers. We have a new concept for a bubble chamber which eliminates the water. That water superheated liquid interface is the likely source of some of the particulate contamination. The particles like to, just like in your bathtub where you get the ring around the top of the tub, the particles like to hang out at the interface. There's also a huge density contrast there. So that interface is bad. It makes it hard to keep the detector clean. We'd like to get rid of it. So we have a new scheme that involves, instead of using water, using a thermal gradient where so the top of the chamber is hot and superheated, and then things get colder as you move down, and at the bottom of the chamber, no more superheating. It's just a normal liquid, and that's where the pistons are. It's mechanically more complicated, but we've made everything larger so that there's more room for neutron shielding. So we think that all of our potential sources of neutrons are now attenuated by another order of magnitude. So the goal here is, it's about the same fiducial volume as the old detector, but the neutron rates should be substantially reduced. And it's a prototype for going to larger chambers. So now this summer the detector is under construction at Snowlab and should be running sometime next year. And so finally then we have plans, and in Canada this was funded last year for a ton scale detector called Pico 500, which the cartoon looks something like this. And Pico 500 will produce a spin-dependent limit on protons similar to what LZ will eventually produce on neutrons. In xenon, the neutron is the odd nucleus out. In fluorine, the proton is the odd nucleus out. So we produce a measurement on protons, they produce a measurement on neutrons. In principle, these can differ by about an order of magnitude. You have to consider, the relative coupling to up quarks and to down quarks and how those things balance out. So these are, in principle, independent limits, although it's hard for them to be in asymmetry by more than about an order of magnitude. And Pico 500, of course, is an order of magnitude smaller in target mass than LZ. So it shows what you can do with a relatively modest-sized target, as long as the target is fluorine. And then this will be in itself a prototype for future detectors, which will eventually go below the neutrino floor for xenon. And if you look back over the long period, this is what we've accomplished. So we reduced we've reduced backgrounds by 4 orders of magnitude over 15 years, and then now we have another modest 2 more orders of magnitude to go. So that's been a fun trip. And okay, I think I'm not sure exactly how long I had to speak, but I think I'm also arriving at my time. Thanks.
We have time for a couple of questions.
In the alpha discrimination plot, do you guys know what causes the 2 peaks for the alphas?
Yeah, so there are two decays in the radon alpha chain, and we think that there's energy information in the alpha decay. We have a paper that breaks down some of that and shows how that works.
Are you applying any machine learning technique for discriminate neutrons?
Yeah, so there is in our last run we had a neural network technique. The neural networks looking at the acoustic signals, and we trained the neural networks on neutron exposure and on a background alpha exposure, and then applied it to the real data. And so that's actually shown on that plot. There's I don't know if I can, let me try to go back there. Oh yeah, here it is. So there's actually this thing called the neural network score, which was useful, but it turned out that since we used it together with just a threshold cut on the acoustic parameter, and since the neural network score, this is an alpha and this is a neutron. It correctly identified most of the alphas at alphas, but it wasn't, since there were no events left after the initial threshold cut, this actually didn't contribute to the final result. But in the future, there is some additional discrimination from that on the acoustic signal. Acoustic signals are really complicated, and I think that there's more information in the acoustics than we're currently able to extract with this simple cut-based analysis.
More questions? Okay, so we can go for the coffee break, and after 15 minutes, we are back. Thanks.
Thank you.
For some reason, we lost.
Well, I put it here.
Oh, you put it,
Yeah.
but it was just not
Well,
working.
it wasn't immediately working, but it might have recognized. Oh, now it's working. Look, it would have worked.
Okay, so for our next talk, probably will recognize that.
Yeah. Okay.